Hey everyone, welcome to our channel. Today, we're going to be talking about chemical process dynamics and control, specifically PID control in the context of closed loop systems with disturbance. Time delay has a very interesting impact on that, and so we will be exploring that. My name is Akiva Stein, and I will be presenting alongside Connor Rutledge and Kathryn Tang. So here's the problem that we're going to focus on today. Consider a closed loop system. Y of S is equal to GP of S times U of S plus GD of S times D of S, where D is the disturbance variable. With the process transfer function, GP of S is equal to 2 over 50S squared plus 15S plus 1. The disturbance transfer function is shown at the bottom of the page, and the PID control parameters are given as well. So the goal is to calculate the final value from A, a unit step change, and B, a unit step disturbance. Then we're going to repeat that and incorporate the time delay, e to the negative s, and compare.
So first, before we begin, let's take a look at the block diagram for the case without the time delay. On this upper line here, you can see how we have our disturbance function, which in this case is a unit step. So that in the Laplace domain is 1 over s. That disturbance is fed into the disturbance transfer function, which in this scenario is equivalent to the process transfer function. On the bottom here, we have our set point, which again is a unit step. So the Laplace domain makes it 1 over s. And here is where we have our feedback loop. So to begin, YSP will go through. It'll go through the PID controller, through the process transfer function. That will be added to the disturbance times the disturbance transfer function. And as that is being output, whatever that value is will be sent back through the system to help correct for any disturbances or general errors that occur along the process. For this first case, we're going to be looking at only when there's a step change in the set point. So we're going to say that D is equal to 0, and that will simplify things somewhat. So like I said, first we're going to solve the case for a unit step change in the set point. So you saw that we had a PID controller, and that can be modeled using the form PID is equal to KC times 1 plus 1 over tau 1 times S plus tau D times S. Since they gave us our values for KC, tau 1, and tau D, we can plug those in and simplify, and we are left with PID is equal to 2.97 S squared plus 1.65 S plus 0.23 over S. Now we can look back at this diagram. We can combine our PID control with GP of S and then balance the block diagram. What we mean by balancing the block diagram is we're going to look at all of these junctions here. So since the disturbance is 0, we're basically going to treat this as just a straight line into the scope, leaving our only junction as this junction right here. So if we look at what we have going in, we have YSP minus Y times PID times GP of S is equal to Y. So of course we can rearrange to solve for Y. We're left with this kind of nasty equation on the bottom, but I promise it will simplify very easily. Since we have this equation, we're going to apply the final value theorem in order to find our final value as time goes to infinity. So our step change is 1 over s, and when you're using the final value theorem, you do the limit as s goes to 0 of s times whatever the Laplace domain is times y. As you can see, that s times 1 over s cancels out. We can simplify this nasty bracket right here, and we're left with this long equation. Plugging in 0 wherever s is, we are left with 2 times 0.23 over 2 times 0.23, which of course simplifies to y when time goes to infinity is equal to 1. Now that we've done that, we're going to look at the case for a unit step change in the disturbance. Just as we disregarded disturbance in the case that we were looking at the set point, In this case, we're going to disregard the set point as we look at the disturbance. So just to reiterate, our PID controller can be modeled using PID is equal to 2.97 s squared plus 1.65 s plus 0.23 all over s. Again, combining our disturbance transfer function and balancing the block diagram, we are left with this equation here. Rearranging to solve for y, once again, substituting 1 over s for d as the unit step change is 1 over s in the Laplace domain, and applying the final value theorem, we are left with this lengthy limit down below. Thankfully, once again, the s times 1 over s cancels out, and then we can plug in 0 wherever we see an s remaining. We're left with 2 over 1 simplifies to 2 times 0 over 0.46, which of course means that the final value as time goes to infinity is 0.
Now we're going to repeat the process, but this time we're going to add in a unit step change with a time delay. So we can model the transfer function using GC is equal to 1 over G of S, which is our given transfer function, times Y over Y set point with regards to the delay, or the delay over 1 minus Y over YSP with the delay. And since YSP is equal to 1, which was given to us, we can simplify this equation slightly to GC is equal to 1 over G of S times Y over 1 minus Y. And we're gonna plug in the given values from the problem statement to get our GC equation, which is 1.65 times 1 plus 1 over 7.12 S plus 1.18 S. And in the problem statement, we are also given our G of S equation, which is 2 times e to the negative s over 50s squared plus 15s plus 1. And plugging both of these equations into the equation we just derived, we're going to get 1.65 times 1 plus 1 over 7.12s plus 1.18s, which is our GC, is equal to 1 over our G of S, which is 50s squared plus 15s plus 1 over 2e to the negative s. And all of that's times y over 1 minus y. And we use Wolfram alpha to solve for y, and we got this huge equation. And using the same final value theorem, we're going to take the limit as s goes to 0 of y. And when we plug in that big equation for y that we got just now, in the numerator, we have left 33 times 125, because 125 was the only value that didn't have an s attached to it, as you can see. And in the denominator, we have 4,125. And when you do 33 times 125 divided by 4,125, you get 1. So this indicates that as time goes to infinity, our y value approaches 1. And we're going to do this, but this time for a unit step disturbance with time delay. And the transfer function can be modeled using D, which accounts for the disturbance, times G of S times Y minus GC times G of S, which is equal to Y. And since the disturbance is 1, we can plug that in and rearrange the equation above to get G of S times 1 minus Y times GC, and that's equal to Y. And now we're going to plug in the equations for G of S and GC into that equation that we just got. And we can solve for Y using Wolfram alpha or a similar online calculator, and apply the final value theorem to that, which is as S goes to 0. And as you can see, the numerator is 17,800 times S, so that'd go to 0. That's divided by the denominator, and we get 0. So as time goes to infinity, our y value goes to 0.
All right, so I know everybody loves modeling process dynamics by hand and working with these cooling equations. But now we're going to get into some simulations to see if we get the same results, because simulations are easier and used in the real world a lot more. But it's important to know the handwriting behind it. So that's why we went over it so thoroughly. Here is the block diagram, which Connor explained so elegantly previously. And the box that looks like your grandparents' television is called the scope, which lets us look at the variable of interest as a function of time after the disturbance was introduced, or the change in set point. So we're going to first look at a plot or the scope of a unit step change in the set point and then in the disturbance variable. Here we see the change in set point, and it arrives at a steady system response at around 50 time units. It looks like we can just call it seconds, or I'll keep it time units. So remember that number, 50. And next, we'll see what happens with the disturbance. That also reaches stability at around maybe 60 units, we can call it. All right, great. We got 50 and 60 units. Let's see what happens when we introduce a delay. So these sign boxes, these wavy sort of curves represent time delay. And right now we're working with a time delay of 1, so just e to the negative s. So here, the shape looks generally the same. And at the start, you can see a horizontal shift of 1 unit. And however, the overall stability of the system doesn't reach like entirely, it doesn't become entirely stable until maybe 60 or 70 time units, which is dramatically more than the 1 unit horizontal shift we had earlier, showing the cascading effect that a time delay can have in the PID loop. Again, we can see the same thing here. It's generally the same shape, but there's not stability reached until maybe 70 or 80 time units. So these responses that we've seen will change based off of the system properties and the signals that it receives. Simulink makes these a lot easier, so we can explore some more differences and some more, and just learn about systems much easier by just plugging in differences and looking at the simulation. Now let's look at what happens if we increase the time delay, and maybe we'll have time to talk about a ramp function too. Now we have a time delay of 5, e to the negative 5s. And look, this is not stable, not at all. It just gets bigger and bigger and bigger. It's oscillating like crazy. You would want to avoid this. So in reality, we would be sure to find what type of time delay would result in stability, in instability, and stay well below that. And we included this last plot. This is what happens when the ramp, when there's a ramp change introduced to as a disturbance. We messed around with the slope. We got it to, we said 0.35 because this made the plot look remarkably similar to the unit step change in set point. Might be a coincidence, it might not, but we found it interesting. The only difference was that it found stability a little bit higher. The stability of the set point was found at 1, but this is at about 1.5. Thank you, and thank you for your time. This was very fun, and we hope to see you next time. Like and subscribe.